These are all in section 4.3. The first test we're going to use is the increasing decreasing test. And the idea is that if you want to know where your function is increasing or increasing, decreasing, you're just going to take the derivative of the function and try to figure out where the derivative is positive or negative. Okay, positive means increasing, negative means decreasing. We're going to use the critical numbers to do that. After we figure out where the function is increasing and decreasing, we can use the first derivative test to tell us where the function has local maximums and minimums. So after we find the critical numbers, um, any critical number at which the derivative changes from positive to negative will give us a local maximum. Any critical number where the derivative changes from negative to positive, so f will go from decreasing to increasing, will give us a local maximum. If it doesn't change sign, for example, if f prime is positive on both sides or negative on both sides, then we don't get our local max or min. So critical numbers don't necessarily imply local maxes or mins. The next test we're going to use is the concavity test. If the second derivative is positive on an interval, then that means the graph is concave up. If the second derivative is negative, that means the graph is concave down. Any point on the graph at which there's a change in concavity is called an inflection point. So we're going to look for those also. And we're going to try to put all this together to do a quick sketch of the graph. Now, the second derivative test here is just an alternative to the first derivative test. If you want to tell if something is a local max or min, you can compute the second derivative and plug that critical number into the second derivative. So this is just an alternative some people prefer. Okay, so let's do one of these. So this is a polynomial function. And let me just get this out of the way. And we're going to sketch the graph of this function, and we're going to break it down using all those tests I just mentioned. Okay, so it says the first thing I want to do is I want to find the intervals on which f is increasing or decreasing. So I'm going to take the derivative. Okay, and what I want to do is I want to find the critical numbers of this function, because I know that the critical numbers are the only values at which f prime could have changed sign from positive to negative or negative to positive. Okay, so let's find the critical numbers. F prime of x let's see, 2x squared. Sorry, 6 times 2x minus 1 times, okay, so I think I factored this correctly. So in this case, we have x is equal to 1/2 or x is equal to -1. And since this function is always defined, it's a polynomial, we don't get any critical numbers due to things not being defined, the derivative not being defined. So these are the critical numbers, okay, of the function. So next what I'm going to do is I know that if the derivative, I'm going to test the sign of f prime, and I know that if the derivative changed sign, it could only have changed sign at -1 or 1/2, because those are the derivatives where it crossed the x-axis. So what I'm going to do next is I'm going to pick a value from this interval, and I'm going to test it inside of my derivative to see if it's positive or negative. So we're going to test f prime of 2, -2. And if you plug -2 into the derivative, then we get the value 30, right? Which is positive. So I know that the derivative is positive on this interval. So let's test 0. If I plug 0 into my derivative, I get -6, which is negative. So in this region, I know that the derivative is negative. It could have changed sign here, so let's check. F prime of 1 is, I believe it's 12, which is positive. So the derivative is positive over here. What this tells me, using the first derivative, no, the increasing, decreasing test, is that f is increasing here, decreasing here, and increasing here. So that's what f is doing. Okay, that's by the increasing, decreasing test. So I'm just going to write that down here as my answer. Is that f is increasing on negative infinity, -1, and the interval 1/2 to infinity, because the derivative is positive, and f is decreasing on the interval -1 to 1/2. Okay, so that's the answer to part A. Okay, so we need to find the local maximum and minimum values of f. I'm going to use the first derivative test, which says that any critical number at which the derivative changes from positive to negative is a local maximum value. So this means by the first derivative test, f has a local max of f of -1, which is equal to, now remember to plug this back into f, not into f prime. So this is going to be 4 times -1 cubed plus 3 times -1 squared minus 6 times -1 plus 1. So that's what I have down here. Plugging into f, that's going to give me -4 plus 3, that's -1, so I get 6. So this is my local maximum value. Also, by the first derivative test, we know that any critical number at which the sign of f prime changes from negative to positive is going to give us a local minimum, okay, at that value. So in other words, f went from decreasing to increasing, so that makes sense. Okay, so f has a local min at f of, let's see, 1/2, and if you plug that into f, you get -3/4. Okay, so remember to plug that into f, not into f prime. Okay, so moving on, part C asks us to find the inflection points of f and where f is concave up and concave down. So remember that the second derivative tells us about concavity. So I'm going to go ahead and take the second derivative of f. Okay, now I want to figure out where this is positive or negative. So I'm going to find the critical numbers, find where it could have changed sign. So f double prime of x is equal to 0 if and only if So now we're going to test the sign of f double prime and try to determine where f is negative or f double prime is negative or positive. So let's choose a value to the left of -1/4. I'm going to choose 1. F double prime of 1, it looks like it's positive. And let's choose a value to the right of this critical number. So f double prime of +1. So this was, oh, this was -1, sorry. So this should be negative. And then over here, f prime of 1 is positive. So we know that the second derivative, f double prime, so we know the function is going to be concave down and concave up here. So indeed, this is going to give us an inflection point because it's the function changes concavity here. So let me just write that down here as an answer. F is concave up on this interval. F is concave down on this interval. And we have an inflection point at -1/4. I know I plugged this in before, but f of negative 1/4 is 2.625, around there. Make sure to plug this into f, not into f prime or f double prime, to get your inflection point, because this is a point on the graph of f. The last thing I want to do is I want to give a really quick sketch of this function using the information we have. The first thing I usually do is I graph the local maxes and mins. So we had a local max at the point negative 1, 6, and we also had a local min at 1/2, negative 3/4. Okay, or sorry, 1/2, negative 3/4. Okay. We also found that the function was increasing over here, decreasing here, and increasing here, and that there was an inflection point at negative 1/4, which is about here, 2.625. So maybe right around here, there's an inflection point. So the graph should be concave down and then concave up. This information helps me to do a really rough sketch of the graph. If I wanted something with a little more accuracy, I could plot the intercepts. In this case, we have a y-intercept at 1. So now I'm going to try to fill in the graph here. So I make the graph so it is concave down and increasing, concave down and decreasing. And then I have the graph as concave up and decreasing, and then concave up and increasing. So that's a quick sketch of the graph.